Okay, let's start with a wild idea. What if you could take a massive, room-sized laboratory and shrink it all down to the size of a postage stamp? Sounds like science fiction, right? Well, today, we're diving into something called Droplet Microfluidics, a technology that's doing exactly that. And believe me, it is changing science and medicine as we speak.
Just look at this. It might look like some kind of abstract art, but what you're seeing is science in action. Those are thousands upon thousands of perfect little droplets. Each one is its own tiny, self-contained experiment, flowing through a channel that's thinner than one of your hairs. This right here is the power and just the sheer beauty of droplet microfluidics.
So to really get why this is such a huge deal, we've got to ask a pretty basic question. You know, we live in a world with all these incredible ideas, but what's the one thing that's always slowing down the next big discovery?
Well, the answer, and this might surprise you, is often just the sheer amount of work involved. You know, traditional lab work, think rows and rows of test tubes and beakers, it's gotten us this far, for sure. But it has some pretty big limitations that can really just stop a breakthrough in its tracks.
I mean, think about the huge challenges we face. You've got to screen thousands of possible new drugs, or analyze just a handful of precious cells from a biopsy. Or maybe you're trying to create brand new materials. All of that stuff takes huge amounts of really expensive chemicals and super rare samples. It's slow, it costs a ton of money, and yeah, it's a massive bottleneck.
But what if there was a way to do all of that, but way faster, way cheaper, and with just a tiny fraction of the material? Well, that is exactly the promise of this droplet revolution.
And at its core, the idea is actually incredibly simple. Basically, you use these microscopic channels to chop up a stream of liquid into millions and millions of identical droplets. And each one of those tiny droplets acts like its own little test tube. It perfectly seals whatever's inside, maybe it's a single cell, maybe it's a chemical reaction, and keeps it isolated from everything else.
And the benefits? They're just mind-blowing. We are talking about running thousands of reactions every single second. Instead of using milliliters of a sample, you're using picoliters. That's like using a single drop of water instead of a whole swimming pool. The savings are huge, and the control you get is so precise, which means your results are more accurate, more reliable, and you get them way, way faster.
Okay, so that's the what, but what about the how? How do scientists actually make and control these tiny little marvels? Well, it all comes down to some seriously clever engineering on the microfluidic chip itself.
Right, so there are basically two main ways to do this. The first and most common is what we call passive. This is where the actual shape of the tiny channels and the physics of how the liquid flows does all the heavy lifting. It's really elegant and pretty simple. Then you have active methods. This is where you bring in some outside force, like an electric field or magnets or even heat, to get super precise on-demand control over making each droplet.
And here are a couple of the most common passive designs in action. Take a look at the T-junction. You've got one liquid coming in from the side, and it just gets sheared off, chopped into these perfect little droplets by the main liquid flowing past. It's that simple. And then there's flow focusing. Here, you can see the main stream in the middle is getting squeezed from both sides. That squeezing action is what pinches it off into these super consistent, uniform droplets. It's amazing, right? It's all about using the shape of the chip to manipulate physics.
Okay, so you've got all these clever ways to make droplets. That brings up a really important question. Which one do you pick? Well, it turns out it all boils down to one fundamental trade-off.
Yeah, this quote from the research really just nails it. The generation throughput is typically inversely related to the droplet size. So what does that mean in plain English? It's simple. The faster you try to make the droplets, the smaller they tend to get. You can have speed or you can have a specific size. But getting both at the same time, that's the real challenge, the holy grail of this whole field.
In this chart, this just lays that trade-off out perfectly. Let's look at crossflow up top. It's simple, but it's slow. Like 2 droplets a second, slow. Now let your eyes jump all the way to the bottom, the capillary T-junction. This thing is an absolute monster. It can crank out up to 80,000 droplets every single second. I mean, that's just blindingly fast. But as you can see, the trade-off is you have less flexibility on the size of those droplets.
So what's the big takeaway here? It's that the method you choose depends entirely on what you're trying to do. Are you screening millions of drug compounds? Then you need that extreme speed. But what if you're trying to capture larger cells inside each droplet? Well, then you might have to give up some of that speed to get the size you need. It's all an engineering decision.
Okay, so this is all awesome for a research lab.
But if we want to take this technology and use it in the real world to, say, manufacture new drugs or create new kinds of materials, we run into one giant hurdle. And that hurdle is scale.
And here is that bottleneck in a nutshell. A single one of these droplet generators, even one of those super fast ones, produces a tiny, tiny amount of material. We're talking less than 10 milliliters an hour. For manufacturing or clinical use, that's nowhere near enough. Not even close. So what's the solution? Well, it's one of those ideas that's both brilliant and perfectly logical. If one droplet maker is too slow, why not use 1,000 of them? This is called parallelization. You're essentially building a whole factory floor of these generators, all on a single tiny chip, all running at the exact same time.
And engineers have come up with some incredibly smart ways to do this. You have things called tree networks. Just picture a river delta, right? The main flow splits into smaller and smaller identical streams, making sure every single generator gets the exact same amount of fluid. Then you have something totally different, like edge devices. For this, imagine water flowing evenly over a very long, straight ledge, creating hundreds of droplets all at once, right along that edge.
And what's the result of all this massive parallelization? We go from those measly milliliters per hour to production rates of 1.5 times liters per hour. And that's just for starters.
This is the key that unlocks the door from the lab to the factory. We're talking about a 100-fold increase in output, or even more. And that means this technology isn't just a cool toy for researchers anymore. It's now a real, viable platform for manufacturing.
And with that leap in scale, the doors just fly open to all these incredible, real-world uses. You can now talk seriously about creating perfectly tailored drug delivery systems, or rapidly screening for new medicines on a massive scale. You can analyze a patient's cells one by one to create personalized cancer treatments. You can even use it to design new kinds of foods and cosmetics. The possibilities are just huge.
So I want to leave you with this one final thought. We now have the power to run literally millions of tiny labs all in the palm of our hand. The technology is there, so the only real limit is our imagination. It makes you wonder, right? If you had this power, what's the first impossibly complex problem that you would try to solve?